Hi, my name is Arda. I am third year student at Electrical and Electronics Engineering Department at Bilkent University. So here I'm going to present my term project for EE412, which is two-stage LNA MMIC design. As a project is required that 28-volt drain supply available to both stages. And this MMIC has an operation band of 6.84 gigahertz to 7.56 gigahertz, and to have a matched load and source impedances to both 50 ohms. And it has to be unconditionally stable, which is required to have a stability factor greater than 1.05. Throughout the band 10 megahertz to 8 gigahertz, and the amplifier should have input return loss greater than 7 dBs in the band and output return loss greater than 15 dBs in the band, and to have a gain variation less than 5 dB in the band. The noise figure should be close to F minimum. The project requirements suggested. So in the first stage, I selected two hunts from Krigan processes, and I choose the bias points at deep class AB operation, and I determined two stages, first stage as LNA stage and the second stage as power gain stage, and in the first stage, I decided to use 2x100 Hemp, and in the second stage, 4x100 Hemp. And as a first step, I traced the IV curves for each transistor, and I determined their maximum gains and noise figures as well. For the first stage transistor, I determined the bias point as follows, and the maximum gain determined in this bias point as 15.3 dBs nearly, and the noise figure determined as 2.6 throughout the bands. For the second transistor, I determined max gain as 18.8 dB throughout the band. So later on, I need to stabilize the transistor, and I decided to have such topology in the first stage. I put stability network in the output side of the transistor because this stage has to be LNA stage. Also, I decided to use source degeneration inductor to increase the noise performance. So the results of the stability network for the first stage can be seen, and the stability network gives us a stability factor greater than 1.057 throughout the required frequencies, and the noise figure noise figure determined as 2.6 throughout the band. For the second stage, I decided to have a simple parallel RC network in the input side of the transistor to stabilize, and I also decided to use inductor in the DC feed line as well. And the stability network gives us stability factor greater than 1.051 as the requirement suggested. And the maximum gain after the stabilization network is installed to this stage determined as 17 dBs. For the first stage, I decided to match for both noise and the maximum available gain in the input side. And output side, I matched for maximum available output power. As you can see in the input side, I have a simple T network, and in the output side, I have a pi network. And as you can see in the following figure, I need to compromise between maximum available circuits and the noise circuits to optimize both gain and noise at the same time. But in the output side, as you can see, the GL circle matched to exactly 50 ohms to obtain highest possible output power. So in the following figure suggests that our noise figure for the first stage determined as 2.3 dBs to 2.4 dBs throughout the band. And for this stage, we need to expect the gain, which is around 15 dBs. For the second stage matching, I simply match the match for a maximum available gain and the output power. So I use two T networks in the both output side and the input side. So here are the results of the second stage matching, which you can see the GL and GL circles exactly match to 50 ohms to obtain maximum available gain and the highest output power at the same time. So here you can see the second stage is a little bit noisy, noisier more than the first stage. But this stage gain is significantly larger than the first stage. So afterwards, I cascaded the two stages simply, but this process changed the both amplifiers S11 and S22. Then the component values needs to be tuned. So after tuning, two-stage amplifier is obtained with ideal components. So for MMIC design, ideal components needs to be changed with non-ideal ones, which can be found in Cree-Gunn processes PDK library. And then layout was generated with updated schematic. So here you can see the updated schematic with non-ideal component values. And you can see the layout, which is created according to this updated schematic, and the final dimensions of the layout determined as 3 by 5 millimeters. So here are the final results. As a final performance metrics, noise figure of 3.4 dBs is achieved, and its lowest point is 3.1 dBs throughout the band. So you can see the requirements for S11 and S22 is highly satisfied, and the final design have a gain variation of 0.9 dB, which is enough to meet the requirements, and this amplifier achieves the nominal gain of 23.6 dB throughout the band. And you can also see the OIP3 performance, which is determined as 42 dBc, which is evaluated by testing the amplifier with two signals separated by 20 MHz. This concludes my presentation. Thanks for listening.